Okay, I'm going to change the gear a little bit and talk about an observational program that we have been pursuing in the past year. And the motivation behind this survey was prior work that I led with one of my former graduate students, Nicholas McConnell and Carl Gebhardt and Todd Lauer, James Graham, and so on, that where we targeted the most massive black holes in the nearby universe. We wanted to measure them dynamically and using ground-based 8 to 10 meter telescopes with adaptive optics. In that program, our selection of targets was quite heterogeneous. Basically, telescope proposal deadline was coming up. We wanted good targets, and then we looked for good candidates to up our chances for detecting black hole masses. So in the back of my mind, there have always been this thought that wouldn't it be nice to have a well-defined galaxy survey of the most massive galaxies nearby, and starting with those to pick black hole candidates. So about a year ago, I talked to Jenny Green, who at that point, she was using also the same IFU at the McDonnell Observatory in Texas, and her observing schedule was often right after hours. So her science interest at that point had been the outskirts of early type galaxies, getting population gradients and metallicity gradients and so on. So we have very complementary science goals, but we were using the same instruments, similar techniques. So I invited her to start the survey. So we have been working hard on this in the past year. So I would like to describe the survey and tell you our recent progress. So very briefly, this is an integral field spectroscopic survey of about 100 most massive, by massive I mean stellar masses, early type galaxies, within a volume of about 100 megaparsec. And it's volume limited, and the galaxies are chosen based on stellar masses via K-band luminosities. Okay. We use a 2-mass all-sky survey, and it's also a multi-wavelength, as I would describe, and photometric survey in addition to being spectroscopic. And the basic thing we're trying to do is to get spatially resolved two-dimensional stellar kinematics to study in detail the formation of early type galaxies from central parts to the outskirts, and to study their central massive black holes. So the science goes, so why will we be interested in these most massive early type galaxies nearby? Why are they interesting? And here are just a few highlights, that they are potential hosts of the most massive black holes. As we heard about, galaxy and black hole are correlated, and bigger black holes tended to live in bigger galaxies. And also they are possibly the quiescent counterparts today of high redshift very luminous quasars. Some of those have been shown to have black hole masses possibly reaching 10 billion solar masses based on more indirect emission line width measurements. And if they were 10 billion solar masses at redshift 4, they can't decrease, they got to be somewhere today. And where are they today? Clearly, they're not sitting in quasars today. So those hosts have become quiescent, the sleeping giants today, and those are possibly early type, most massive early type galaxies. And also, these are possibly descendants of some of the galaxies we've been hearing about in this conference and tomorrow and so on, of the redshift 2, either massive star-forming galaxies or the compact red high stellar mass galaxies. They could possibly evolve into the most massive galaxies today. And also, this is probably a topic for a different conference, there are sites of possibly varying initial mass functions. There have been a lot of recent discussions about that. So these are just some reasons why we would like to study these galaxies better. So then why another galaxy survey? We have heard so much about galaxy survey, this survey, that survey. So I would like to sort of contrast, so what's the parameter space our survey is targeting? So first of all, you would think Sloan has covered everything nearby. Not so. Okay, out of these 100 galaxies that we carefully selected, in fact, only about 65% of them have SDSS photometry, not even spectroscopy. Okay? Because some of them are so big on the sky that it wasn't even targeted by Sloan, or they're not in the Sloan footprint. And also only 25% actually have Sloan fiber spectra. And just for comparison, I'm going to talk about IFU spectroscopy over about 100 arcsecond field of view. Even when they have Sloan spectrum, that's one fiber of a width of 3 arcsecond, because we cover much wider field of view. And it may have come to your mind that there is a wonderful early type galaxy survey of the nearby local volume, and that's the ALICE 3D survey. And they targeted 260 galaxies, again, IFU, very detailed kinematic studies, and they have a wealth of publications. And I will show you the parameter space we stand relative to ALICE 3D. Only 6 out of their 260 galaxies are in our survey, and the reason is their volume is very small. It's 42 megaparsecs. And there's a SLUG survey that's being conducted here and so on. And again, only 2 out of the 25 galaxies are in our survey, and slugs are chosen from ALICE 3D. Okay. And I will show you something about the environment of the galaxies we live in. And interestingly, you would think most of massive galaxies should sit at the centers of clusters. Not so. Okay. So briefly about the sample selection, we've spent a lot of time on carefully selecting the sample. So this is where we started out with 2 mass extra source, extended source catalog, and we chose an absolute K cutoff of minus 25.3, anything brighter than that. And the corresponding stellar mass is about 10 to the 11.5. So these are some of the most massive galaxies nearby. Okay. And in contrast, I've put down the ALICE 3D's selection. Again, our selection is similar in that it's volume limited and stellar mass selected. And volume limited, and we chose 108. The reason is we would like to obviously go beyond Virgo, and Coma is conveniently at about 102. So we thought, okay, let's go out to beyond Coma. And within this volume with that K selection, it gives us about 100 galaxies, a pretty good statistical sample. Okay, morphologically, we use hyperlida and we put a cut on early types. We don't want to get into the details of E's versus S zeros, so we include anything that's E or S zeros, and that led to about 100 galaxies. And again, in contrast to ALICE 3D, when they went from Sauron to ALICE 3D to increase their sample, they picked up a lot of fast rotators. Whenever you hear their talk, they say early type galaxies are not necessarily the slow ones. In fact, most of them are fast rotators, and the reason is they are picking up the lower mass galaxies that are mainly S0s. For us, most of our galaxies are ellipticals, and there are a handful S0s. And there are some additional criteria on extinction, and obviously we're in the northern sky. Okay. So the instruments we've been using we use an assortment of spectrographs, and the reason is we would like to have a very extensive spatial coverage, both in terms of being wide field and high resolution. Okay. So the working instrument is the Mitchell, it used to be called the Virus P. Now, thanks to George Mitchell, has been renamed for the donor of the instrument, the integral field spectrograph in Texas. And here is their publicity slide showing the extent of this IFU. It's one of the rare instruments that has such a wide field of view. And so it has 246 fibers. So in one shot, you get spectra for 246 spatial parts on the sky. And each fiber is thick, it's 4 arcseconds. Okay? And the wavelength coverage is in the optical. And because of this nice spatial coverage, we can get to about 2 effective radii for half of our galaxies, obviously depending on how big these galaxies are. So that's a very important information we would like to get. Complementary to that, we would really like to get to the central part. 4 arcseconds clearly is way too big to study black holes. So for a subset of these 100 galaxies, we select the appropriate ones for follow-up ground-based plus AO observations, zooming into the very, very center part. You can see from about 0.1 arcsecond to 3 arcsecond, depending on which instrument we use. Okay, and these are very expensive observations, and there we combine the data to do short-shot modeling to determine the black hole masses. Okay. And in addition, we also need photometry for a lot of the studies. So especially the K-band coverage of two mass is very, very shallow. Okay, so for these galaxies, you will worry that their total luminosity is probably underestimated. So we have a follow-up deep K-band survey right now where the data are pouring in right now on CFHT and UCURT just to sit on these galaxies longer to get a better measurement. And we need HST photometry for the black hole modeling and so on. Okay, so it's a photometric survey too. So let me just show you 3 slides highlighting where our galaxies are in the parameter space. Okay. So here is a simple distance versus absolute K-band magnitude plot, and contrasting our points, the massive survey, to ALICE 3D. Okay. As I mentioned earlier, ALICE 3D is volume limited out to 42 megaparsecs. So you can see you put a cut horizontally like that, and there's is K-band limited to minus 21.5. So you can see these are the galaxies they picked out, and we've highlighted M87 here. But when we enlarge our volume to 108, obviously massive galaxies are rare. So if you want to have a lot of them, you got to increase your survey volume. So these red ones popped out. Okay, obviously there are a lot of things in the blank spot we're not targeting. We're targeting the most massive ones. Okay, and that's why there are only 6 overlaps, because ALICE 3D's volume is very small. Another way to put it is almost all of our galaxies lie beyond 42 megaparsecs. Okay, and we're highlighting just for orientation the 2 big galaxies. NGC 4889 is the biggest one in our survey, and that's the BCG of Coma. Okay. And again, I want to just show these are K-band magnitudes from 2 mass. Probably many of these are underestimated. Okay, so with our deeper K-band, these points are going to move towards the right. But these smaller ones, probably the K-band magnitudes are pretty robust. This is the Faber-Jackson relation, again, to highlight the velocity dispersion versus luminosity, okay, relation. Again, I want to emphasize our selection has no cuts on velocity dispersions. Many black hole studies tended to target high velocity dispersion targets. We didn't want that. Okay, we just want simply stellar mass limited survey. And these are the sigmas from hyperlita. We would like to improve. I mean, eventually our kinematic study will improve on all the sigmas. Okay, this is what's in the literature, and some of those are obviously not quite accurate. In fact, there are many measurements that don't agree with each other. Hyperlita is just a compilation of the literature. Okay, again, I want to show that the range of sigma we cover is actually pretty large. Okay, the small ones go down to about 200 kilometers per second. Again, we are going to have a spatially resolved measurement of sigma. So eventually our sigma should be more robust than these. But this just shows you where things are. And another one I'll show is the size-mass relation. Okay, so again, this is a K-band magnitude, and here is the 2 mass. One of their effective radius, there are like 25 of those. Okay, and in our paper, I'll actually highlight our survey paper have been posted on the archive. So we have a plot showing the K-band RE versus Sloan optical RE, and generally you need to boost the K-band RE by about a factor of 1.7. Okay, but don't worry, everybody is multiplied by 1.7 using the 2 mass effective radius for each galaxy. And again, I want to highlight that we're at the very massive end, and look at how large these galaxies are. Okay, these are in kiloparsecs, so they go out to the 1 RE could be tens of kiloparsecs. Okay. Environment. So what we have here are 2 mass selected galaxies. So what we did was, I was very curious to know, are these galaxies sitting in massive groups or clusters? Okay. Or you can back off and think, within 100 megaparsec volume in the northern sky, which clusters can you name? Okay, Virgo, Coma, Perseus. There's some Fornax, I guess it's kind of south, right? You kind of run out of names pretty soon. You kind of wonder, okay, who are the next ones? And so the thing we did was we went into the Crookes catalog. It's a group catalog based on the 2 mass redshift survey constructed by John Hawker et al. So they followed up on the 2 mass photometric survey with a redshift survey, a very nice sample. And then Kirk did a friends of friends linking of the velocities and the transverse spatial distance to pick out groups. Okay, this is a standard way of choosing groups. There are obviously problems with groups of very few members. Some of these low ones are 3 or 4 members. Okay, but we just use their catalog. And this is what we found for our galaxy. This is distribution. And here is a halo mass that these galaxies live in. Again, caveat, right? The standard way in the optical, when you try to, or infrared, when you try to infer black hole mass, you can use the virial mass estimator. There's a projected mass estimator based on the velocity dispersions and the relative separations. So, you know, they're probably, weak lensing would be better, but this is what you can do traditionally, and this is what the halo mass that our galaxies span. But I want to highlight one thing is there are 26 galaxies in our survey that have no groups in this catalog. Okay, they are isolated, obviously, in quotes. We all know they can't be completely isolated. You got 2 masses, again, it's shallow. So if you go deeper, there got to be satellites. But it's interesting that such a massive galaxy, right, there's nothing in the 2-mass catalog. So we're looking to Sloan, and I think it would be interesting to find the second most luminous galaxies, for example, in those groups, whether they could be fossil groups and so on. Okay, a few of our galaxies are well-known fossil groups where the magnitude gap is very large between the 2 brightest galaxies. Okay. Another thing I want to highlight is the difference between the black and the red. Okay. So the black is just a distribution of the halo masses, but the red are the ones in our galaxies that are the brightest galaxy in that group. Okay, so you can see for the lower masses ones, all of our galaxies are the brightest galaxy in that group. But when you go to the higher masses, the difference between the black curve and the red curve, those are the ones that are not brightest group galaxies. Okay, even at this mass range, this is very, very massive, about half of these galaxies at this more massive end, they have a companion in that group that's even brighter. Okay, and so studying people who survey brightest cluster galaxies, that would be a different selection from our survey, which is not selected based on environment, right? Again, we're selected just based on stellar mass. Yes? No, sorry. So, the difference here are the ones that are massive in our survey, that they make into our survey, but they are not the brightest galaxy in that particular group. So they have a companion, which is also in our survey, that's even brighter. Yes.
So this means that they are brighter in side B, or where are they brighter? In a lower plasma that might be?
No, they're just a few. Some of these groups, they have 2 or 3 galaxies that are bright enough to make into our survey. That's all I'm saying. Okay, so not every galaxy is the brightest galaxy in its own group. Because I know, no, I'm not choosing, right? I'm just including everybody that's brighter than minus 25.3. And it turns out, interestingly, that some of these actually belong to the same group. For example, coma 4889, 4874. Those are 2 bright ones. They are bright enough, right? One is a BCG, the other one isn't. Okay, so I can. That's right. So very good. Coma has 4. Virgo has 3 or 4. And that's about the most number we have. Okay. Okay, so again, just to show you some image, this is a SDSS. Again, only 75% of our galaxies actually have SDSS images. Okay, and we had a debate within the collaboration whether we want to show the montage in the paper. Some people said they're too boring to show; it's just blobs. And then we decided to show them, and they're actually I thought they're lovely to look at, and there's some actually pretty complicated structures here. Okay, although the colors obviously are quite red. Okay, so one word about the survey status. Okay, we started talking about this about a year ago, and it took months to just decide on the targets. But since we have been using the instrument for our black hole studies, and Jenny had been using it for her study, so we had some prior experience. So that allowed us to go fairly quickly. So the entire sample defined by those and the criteria I gave you earlier contain 116 candidate galaxies. And we put the somewhat brighter ones at the high priority targets. Okay? And we have IFU data now for already about half of them, 50 plus. And most of the data are reduced now. And we are now extracting stellar kinematics, making maps. And then we're running mock tests and orbit models. We probably would like to run short-shell model for every galaxy. That's pretty expensive. We're also testing against Jeans model just to see. Okay, I'll show you one preliminary result. And stellar population gradients and so on. Okay, and for a subset of these, we have identified about 20 candidates for black hole measurements. So within the massive survey, 7 of these have already been measured, the black hole masses, by us and others. And we have 5 others in hand already with data, and we're about to publish 2 or 3 more. Okay, so let me just show you what the spectra look like from the Mitchell IFU. Again, this is in the optical, and this is for NGC 1600. It's one of the most massive galaxies, and is one with the largest core in the surface brightness. It's a 6 arcsecond core, according to Lauer, Sandy et al.'s paper. Okay, this is one of the ones we looked at. And I just want to show you that this is ordered in sort of radial bins. So the central fiber clearly has very good signal to noise. And when we go outward, we start to bin up the fibers to, we'll have a criterion of whatever, 20 or 30 signal to noise for different purposes. And the PPXF fit to, based on stellar templates and so on, do a very good job. So through this step, we can then PPXF, that's what Alice 3D, Michela Cavallari et al. Wrote to do this kind of extraction, allows us to make a kinematic map. Because what PPXF does is, from the obviously convolution of stellar templates with the observed absorption lines, you can determine velocity moments. Okay, so not just the radial velocity and sigma, which are the 2 lowest moments, but we also want to get the H3, H4, the higher Gauss-Hermite moments, which tell you about deviations from Gaussian. Skewness and the boxiness, those are very useful kinematic information. So let me show you the kinematic map we obtained for NGC 1600 based on just the Mitchell data. Okay, so this is on the sky. You can see the fibers, and again, it covers out to about, you can see the field of view is 100 arc seconds. There's a radial velocity, not much rotation. Okay, I think most of our are gonna be slow rotators. Sigma is here. You can see very healthy. This is very high velocity dispersion. In fact, this is an interesting rise. Because of its large core, we think we may be detecting the black hole mass already just using the Mitchell spectrograph. And the higher moments are very important for social modeling. This is skewness. That's the boxiness of the velocity distribution. Okay, we're actually testing H5 and H6 just to see if we have enough signal to noise for those higher moments. Okay, so let me just last couple slides highlight. These are just some of the survey sciences we can get out of it, in addition to black holes. Okay, so again, this is Jenny's earlier paper based on smaller mass elliptical galaxies. We can hopefully measure the population spatial gradient within galaxies. Okay, how does that change, or does it change with the function of radius? And this hadn't been studied very well in the past. And then, of course, the mass to light ratio, whether there is a steepening in the IMF when you go to the more massive galaxies. Again, you can see most of the steepening is happening at a more massive end, and that's where exactly we lacked data. So massive should be able to fill in that gap. And then the black hole sigma relation, I just want to highlight this since we saw this earlier. I just wanted to say that when theorists say we can match observation perfectly, just remember observations don't match each other. So now I'm starting to do some observations, and the slopes are all over the map. Okay, and this is our compilation. And I don't want to go into details here, but this is M sigma for all the kinematically measured local black hole masses, and I really advocate that we start to look at early types and late types separately. Okay, these are the two fits. If you do them separately, red and blue, you can see the slopes are relatively steep, although the late types are, the correlation is not very good. The error bar is very important. Okay, epsilon is an intrinsic scatter. And you can see the slopes are roughly 5, although there's an overall normalization offset of 2. Okay. But I don't want to get into details here. But again, this is same plot, M sigma and M, this is versus, sorry, it's a K-band magnitude from Cormandy et al. This is from our paper. Just highlighting where the massive measurements are. Okay, so these are the measurements of the galaxies that are in the massive survey. And clearly, we would like to really fill in that upper envelope just to see what's happening there. Okay. So let me summarize here. So the massive survey is in progress. And we're targeting a new parameter space that had been little explored previously. And the deep K-band imaging should be quite useful for just getting the K-band luminosities right. And we have auxiliary programs right now. For example, 1/3 of our galaxies are in Hubble and Chandra archival data. So that's very useful for studying, so combining wavelengths. And also we're preparing a plateau de Boer proposal to check whether some of these may have CO gas. As some of you may know, there was one beautiful CO gas measurement of black hole mass in early type galaxies last year. Obviously, they're far and few in between, and you need to have CO that's really beautifully in disk configuration around the black hole. That's very hard to get, but if you can get it, it opens up a new tool for measuring black holes. Okay, just in case you wonder what's massive. We kept going back and forth about what to call this survey, and we thought deep. It's very nice, but deep actually is an acronym for something. So we try to come up with an acronym for massive, whatever you want. And so since they're so massive, it's just simply massive. We thought that's good. Okay, thank you. Yeah, it's because they cover different range. So the massive ones, the early types are the red and the green. Green are the BCGs of the, so that tended to cover the higher velocity dispersion part. And our new points tended to pull it up. Okay, and then you add in these Mazur's points, which are the triangles, blue triangle, and they tended to fall below. So if you fit this naively as one population, you get a really steep power law. And then if you try to separate them out, it's a little less steep.
We have these slow fibers for some of them at least. Are you able to tell what fraction are already in the part of the T diagram indicating lighters or some sort of activity? What fraction already active at some level?
That's a good point. Let's see. I don't have that number here. We did look into radio, and there are quite a few with powerful radio point sources. No broadline AGNs. I will have to look at the Sloan BPT. Yeah, I'm not. Most of them have very, very weak emission lines. O3. I mean, a few have O2 actually. So we're looking into that.
A couple comments. First, the turn up there at high velocities has been noticed before, and I know you're very well aware of that. And there's no turn up when you use luminosity, and that's because the relationship between sigma and luminosity is changing for the brightest galaxies. And actually, I think, in my opinion, you and your former student, Boylan Colchin, explained that as a result of interactions and mergers of intense clusters. The second point I want to make is a question. How far to the red does your spectrograph go?
Yes, it's not very red, so about 5,800.
So there's no chance in your making these IMU measurements of the IMF sensitive features?
So we have been thinking very hard about that. So for a subset of them, we actually have GMOS data for the black hole, and those cover a calcium triplet very nicely, and the sodium, right? And so you want to go further, you want more red, and we are scratching our heads about using fire or some others. It seems very controversial, so I'm.
In my opinion, you have to get to the Wien-Ford band.
Okay, I thought Wien-Ford band now has been shown not to be as important, but.
Some people say that.
Exactly, okay, right. So we are trying to make up our mind whether that's worth doing or not because of the controversy. We are thinking very hard about it.
Okay, maybe we can talk more.
Yes.